All right, so we have seen pen and paper methods and we talk about machines, so it is now a good time to talk about modern ciphers where we use computers or hardware and so on. So we start with, of course, encoding because we have to transform our letters, characters into digital representations. So in the digital world, we use bits. A bit can be either 0 or 1. And generally, we represent a character with a single byte, which is 8 bits. Okay. So historical ciphers mostly operate on letters since they are pen and paper methods. When working with digital data, we can represent letters, numbers, symbols, etc. as strings of bits. Thus, the communicating parties must first agree on an encoding, for example, ASCII, UTF-8, and so on. So this is important because if you don't agree on the encoding, it will be very hard for you to perform cryptanalysis. So an example we have seen was in the Enigma. Initially, I told you that British couldn't decrypt them because they didn't understand how the encoding works. But Polish mathematicians, since they knew German, they had the British people to, translate the digital to the characters. Then, British people, mathematicians came up with the idea of breaking Enigma. Similar thing happened actually in differential cryptanalysis. When Biham and Shamir discovered differential cryptanalysis, they actually broken a few ciphers, including Japanese ciphers. So they asked Japanese designers to send, a few cipher text and plain text on a floppy disk, so that they can, capture the secret key from there and send them back. And this happens in 1990, so they didn't have the, at the beginning of at the end of 1980s and so on, they didn't have the internet, so they were sending floppy disk by a postal service. And since the magnetic detectors actually erase the data on the floppy disk, so they had to write it that they shouldn't be, put inside in magnetic field detectors and so on. But at the end, when they received the floppy disk with data on it, they couldn't break it because it was the floppy disk was created on a Japanese machine where they were using a Japanese encoding. So Biham and Shamir asked them to use a computer where it is, it uses an American keyboard and American encoding and so on. So it took like a few months for them to obtain the data, decrypt it, and capture the secret key and so on. So we have to agree on the encoding. So ASCII table is something like this. You 1 byte represents 8 bits. So 8 bits means you can represent at most 256 values, starting from 0 to 255. So this way you actually represent digital data. So we work on bits. So these are integer representation, but generally we work with, bits, not the hexadecimal or the integer values. So assume that we agreed on the encoding, we can represent all of our data as bits. Now you have to focus on what kind of cryptographic algorithm you are using and what the key size should be. Because now in the pen and paper methods, we have seen the importance of the key space. Now we are going to talk about what should be the key space in modern cryptography. So there are some algorithms like hash functions which do not use secret keys, but symmetric and asymmetric key cryptographic algorithm uses secret keys. So in the symmetric key encryption algorithms or secret key algorithms, they use the same key material for both encryption and decryption. This is why they are called symmetric key encryption algorithms. So in this category, there are algorithms like block ciphers and stream ciphers where you perform encryption. But there's also a message authentication code, which is not an encryption algorithm, but it uses a secret key to provide authentication of the data. Okay. So of course, now the question is, what should be the length of the secret key? So we will answer this at the end of these slides. Okay. So let me give a little bit information about how these algorithms work and what kind of algorithms we use in the past and so on. So block ciphers and stream ciphers are encryption primitives, while the message authentication code is used for data and data origin authentication. We can use a block cipher to build both a stream cipher and a message authentication code, or even a keyless hash function. So it is important to know how to break one of these, because since you can use a block cipher as a hash function, for instance, you can find weaknesses in the block cipher which can turn into collisions when you use it as a hash function. The asymmetric crypto systems are somewhat different because there are different types of algorithms in asymmetric key cryptography, and they include like key agreement algorithms, public key encryption algorithms, digital signature algorithms, and so on. So in the symmetric key crypto systems, you have the secret key, you use it for encryption, and you use the same key material for the encryption. So in order for you to communicate, you have to give the secret key to the person you want to communicate through a secure channel. Okay, so you only have a single key material for encryption and decryption. In the block ciphers, the idea is as follows. Block ciphers operate on b-bit blocks of data. Plain text is divided into b-bit blocks. Each block is encrypted by a secret key K to produce b-bit output. Output blocks form the ciphertext. Thus, a block cipher and the chosen key is actually a permutation from 2 to the b elements to the 2 to the b elements. So block size b can be 64 bits or 128 bits. These are the values we use nowadays. And for the secret key size, we recommend at least 128 bits. But if you have longer term security, like military grade security, we are recommending you to use 256 bits. Of course, you might ask that you heard algorithms that use like 80-bit secret key and so on. Are they secure or not? So I will answer them at the end of the slides. So let's start with data encryption standard, DES. It is no longer standard. This is important because people think that this is still standard and still using it, but actually it should be, people should have stopped using it since 1990s. Okay, so it was designed by IBM in 1970s based on an earlier design by Feistel in 1976. NSA tweaked the algorithm by changing its S boxes. So this is actually where this course comes into play, because changing this S boxes modified its security against differential cryptanalysis, which we are going to analyze in this course first. Okay, so this is important. So the DES had a block size of 64 bits, but the secret key was very short, 56 bits. Okay, and this was actually tweaked by NSA because IBM at the time were using block ciphers like Lucifer, so which had 128-bit secret key. But NSA, reduces to 56. So this modification actually made the algorithm weak because they had enough computational power to perform brute force attacks on 56 bits. But they modified the S boxes. But this modification was a good thing in terms of security because the S boxes of IBM was not secure against differential cryptanalysis. But NSA knew that technique at the time and strengthened the S boxes by changing them. It has 16 rounds. It's a Feistel cipher, currently known as data encryption algorithm, DEA, since it is no longer a standard. Became useless after 1990 since its short key is susceptible to brute force attacks. Okay, so the design is very simple. This is a very traditional Feistel cipher. This part is key schedule, and this part is the encryption of one block with DES. Idea is as follows. You have the secret key. You perform some permutation on the bits. You perform rotations to produce round keys. Key 1, key 2, key 3. And this is XORed with the value here. In the encryption part, you take the plain text block, which was 64 bits. You perform initial permutation, which has no cryptographic importance or in terms of cryptanalysis. So the right part becomes actually right 32 bits becomes left 32 bits in the next round without any modification. But the value of the right part is fed into some functions like expansion and key XOR, and here some SBox and permutation, and the result is XORed with the left part. So you actually modify the left part after the first round, but left becomes right in the second round. So now this unmodified R1 here actually modified after the second round. So this way you continue and produce the ciphertext. So as the cryptanalyst, our aim is to break the cipher, right? So our aim is to actually capture the key without knowing the key, of course. So our aim is to capture a lot of ciphertext and, if possible, corresponding plain text. So we wouldn't know what happens inside this. I mean, we know what the algorithm looks like, but we don't know the values of round keys, so we don't know what happens here. So by just using plain text and ciphertext, question is, can you capture the key? So a block cipher, a securely designed block cipher, shouldn't leak the key information from this plain text and ciphertext. But we will see methods how we can do it. Okay. So let's focus on this part. This is the round function part. Right part 32-bit comes here, and the output is also 32-bit and XOR the left part. So let's look at what happens here. Initially, 32-bit is expanded to 48-bit, so some bits are duplicated. Then 48-bit round key is XORed with this 48 bits. Then S boxes are used, so there are 8 different S boxes which take 6-bit input and provides 4-bit output. So this way you are reducing 48 bits again to 32 bits. Then you perform permutation on this 32 bits. So this part is where NSA modified. So IBM's S boxes were not strong, so NSA modified them without any explanation, of course. So let's talk about NSA's involvement. In 1976, NSA tweaked IBM's initial design by changing these S boxes, but didn't explain to IBM why they made such a change. IBM people analyzed this tweak, and they discovered an attack that breaks the initial design. They call it the T attack. By T represents the word here, tickle, because they do small changes in the input, and they observe those changes in the output. They shared their discovery with NSA, saying that they can, break the initial version, and NSA asked them not to share this knowledge with public, for they had known this attack type for some time and were using it to listen to other countries. So this happens, as you can see, during 1970s. Biham and Shamir's rediscovery of differential cryptanalysis in 1990s is the first public announcement of this technique. Okay, so a lot of secrecy agencies knew this technique, but they kept to themselves. As far as we know, Japanese knew it during the Second World War, but didn't publicly make it available. But academicians discovered it, Biham and Shamir, during 1990s. And for this reason, actually, Biham gave a talk when he became ASCII fellow. So he gave a talk titled "How to Make a Difference." Here, difference actually is important because in differential cryptanalysis, you make small differences in the input. So he thanked every secrecy agency who knew this technique but didn't publicly announce it. So this way, Biham had the honor to, be the first person to publicly announce it. So main idea in differential cryptanalysis is to find a weakness, a statistical weakness here we're talking about, so that a small change in the input provides an anticipated change in the output with high probability. So this is how it works. Okay. So let me give you an example with present here, and we will talk more about present and how to apply differential cryptanalysis on present in the following lectures. But I want to show it to you to show you that there are still algorithms, IOC standards, that have short secret key. So present is very simple design. It is designed for lightweight cryptography. This is why the design is very simple. And it is designed for hardware, so there are many bit operations here. The block size is 64 bits, so there are actually 64 lines here, each line representing a single bit. So I'm trying to actually show you how a block cipher actually works with this simple example. So it's around, this picture is just a single round of present. It shows you the key addition, substitution, and permutation layers. And this picture is repeated 31 times. Then at the end, you perform a final key, round key XOR here, okay? So let's look at what happens. You have the 64-bit input, you have the 64-bit round key, which is generated from either your 80-bit master key or 128-bit master key. So you XOR them. XOR is just, the addition modulo 2. Then there is an S box. I mean, there are 16 S boxes, but they are identical. They take 4-bit input and provide 4-bit output. And this 4-bit input and 4-bit output can be seen from this table. So when your input is 0 in hexadecimal, which means that 4 0 bits here, 0, 0, 0, 0, the output is C in hexadecimal notation. So as an integer, C is 12. And if you convert it into bits, you will realize that it will be 1, 1, 0, 0. So this is this kind of a change. And the security, actually, the cryptographic security in a block cipher comes from this confusion layer. So in this cipher, it relies on this, strength of this S-box. So you have to choose it in a very clever way. And in the differential cryptanalysis, we will check this security of a S-box by, creating a difference distribution table and see if it is good or not. Okay, so it is as simple as that. You replace 4-bit with 4 bits here. Then you change the positions of the bits. This is the rotation part, bit rotation. Permutation, actually, sorry, not a rotation. So this is a single round. You repeat this process 31 times. And, question is, this is an IOSS standard, and it allows you to use 80-bit secret key. So question is, can I make a brute force? Because when I talk about this, I said that it has a 56-bit secret key, and we can perform a brute force attack on it since 1990s. So question is, now we are in 2023, our computational power is it enough to break 80-bit keys? And the answer is yes. This is why you should use 128 bits. I will briefly explain in a second. So what should be the key size? An attacker that captures a single ciphertext can try to decrypt it with every possible key to check if it provides a meaningful plaintext, right? Or better, if you capture a plaintext and the corresponding ciphertext block, you can simply, check if it is the one you are trying. Such an attack is called exhaustive search or brute force attack. Exhaustive search is a generic attack. In other words, it is valid for every cipher. Regardless of how you design it, once you choose a secret key, its size actually determines the number of attempts you need to do for the exhaustive search. So for a k-bit key cipher, the attacker is required to perform at most 2 to the k encryptions, or decryptions depending on if you are encrypting the plaintext or decrypting the ciphertext. But the thing is that you have to perform at most 2 to the k operations in terms of encryptions. Thus, security of a block cipher is upper bounded by exhaustive search. In other words, 2 to the k encryptions. This quantity is referred to as time complexity. So aim of the cryptanalysis is as follows. Since we can break every cipher with this many operations, the cryptanalysts try to break the cipher or its reduced round version with a time complexity less than 2 to the k encryption. So if we can break a cipher with less than 2 to the k encryptions, then we say that you broke it. But of course, if it is very close to 2 to the k, we say it's an academic break. But if it is very small, so that you can practically perform on your computational devices, then we say it is a practical attack. So there are the attacks that break this. So let's look at the security of this. Biham and Shamir provided the first theoretical attack, differential cryptanalysis on this, which requires less time than exhaustive search. However, the attack requires 2 to the 47 chosen plaintext to be captured, which is unrealistic because you have to listen to the communication and you should know the chosen plaintext and so on. So this number is huge. So this is because NSA changed the S-boxes, by the way. If it were IBM's initial S-boxes, then Biham and Shamir would break it in a more practical way. But in 1994, Matsui provided the first experimental cryptanalysis of this by introducing linear cryptanalysis. And in the linear cryptanalysis, you don't perform chosen plaintext attacks. You just look at the input and output, in other words, plaintext and the ciphertext, and you have an idea about the XOR of some of the bits corresponding to some bits of the plaintext and the ciphertext. So he really performed this experimentally. He were working at Mitsubishi at the time, and as far as I know, he's still there. So at the weekends, he used every computer in the building. He created many plaintext and ciphertext using a secret key. Then he forgot the secret key and tried to capture it from the plaintext and ciphertext, and experimentally he obtained it. But of course, it still requires many plaintext and ciphertext. In 1997, there was a project called DESHAL. Around 78,000 PCs connected by the internet breaks a message encrypted with DES for the first time in public. So it was a project that's a software you install in your computer, but you have to be connected to the internet, and you allow your CPU power to be used by this project. And then there was a machine designed for breaking DES, EFF's DES cracker. This was a machine containing around 2,000 custom chips, which can break DES around in 56 hours. In 1999, DES is only allowed in legacy systems, so people moved on to triple DES, which actually using DES 3 times consecutively. But in 2002, the AES competition concluded, and the winner, the algorithm Rindal, now is called Advanced Encryption Standard, AES, and it became effective. So again, now the question we have to answer, how hard is the exhaustive search? We said that DES had a 56-bit key. So question is, how large is the key space? So there are at most 2 to the 56 different keys, right? And that number is this. Now I show you present and told you that it allows to use 80-bit key, which is still ISO standard, and it allows 80-bit key. So 2 to the 80 is this, okay? But I also told that present allows you to use 128-bit key. It is this. Also, advanced encryption standards, the minimum key it supports is 128, but it also supports 192 bits, but also supports 256-bit keys. So as you can see, they increase exponentially. So it is also important that the difference is really huge. For instance, think about it this way. Assume that we have technological advance at some point, and we have a very huge, very fast computers, and assume that when we use all of the computational power in the world, we can perform 2 to the 128 encryptions in a single second. So we can break 128 bits security in a second. So still, this wouldn't actually threaten the other ones, 192, because if you can perform this many operations in a single second, a year has around 2 to the 24 seconds. So this means that in a year, you can perform at most 2 to the 150. So you need around 2 to the 40 years to break this one, even if you can break this in a single second. Okay, just I'm trying to show you the difference between these numbers. And more important, that this number is approximately equal to the number of atoms that you can see in the observable universe. So it is really a huge number. Okay, so most probably without any new technology, we won't be able to break this with our classical computers. So we say that these three are secure today. We say that 56-bit DES wasn't secure since 1990s. Question is, can I break 2 to the 80? So 80-bit security is good enough. So how you can check it? You can use your computational devices. You can use CPUs to break, perform a brute force attack on 80-bit key. But of course, we have GPUs, which are very nice in performing parallel operations. And in this case, since we are trying every different key, so you can use all of your GPU cores to try a different key. So you can obtain more than 100 times faster speeds than a CPU. But of course, you can also use FPGAs. And if you have a very nice optimization for an FPGA, you can burn it into silicon and obtain an ASIC, which is a dedicated hardware. It can only perform the implemented algorithm, but they are very cost effective. So if you provide ASIC for an 80-bit algorithm, you can actually break it. But I will show that it is even susceptible to be broken for GPUs, because on a modern GPU, it is possible to try around 2 to the 33 keys in a second for many block ciphers. So it depends on your optimization and how hard the operations inside the block cipher. So let me show you some examples I obtained in the last year using GPUs. So I tried to perform an exhaustive search attack for DES. For instance, on this GPU, I obtained around 2 to the 32 key trials in a second on this GPU. Okay, so if I can perform 2 to the 32 in a second, I need around 2 to the 24 seconds to perform the attack. So it takes less than a year on a single GPU to break this. So if you have thousands of GPUs or millions, then you can even break it in a few hours. So what happens for the present? So since present have more runs, my optimizations didn't achieve as fast speeds as this. But still, this number is huge, and now we have the current series of 4000, which doubles or triples this result. So if you run it for a year, and if you have millions of GPUs, you can actually break present, which has the 80-bit secret key. So this is a problem because if you can do it with GPUs, which is a generic purpose device, I mean, we need millions of GPUs, but if you provide ASICs for it, then you can break it with less than millions of ASICs, because ASICs are really cost effective, and actually they perform more operations in a second, but they also consume less energy. This is why Bitcoin miners are using ASICs. And for the AES, these are the results I obtained. So as you can see, I obtained better results for AES because it was easy to fit inside the GPU architecture. So honest, this 2-generation-old GPU, I obtained this many. I can try this many secret keys, but of course, trying 2 to the 128 would not be possible, even if you have trillions of GPUs. So this is why we are assuming that these key lengths are secure. Okay. One final thing is as follows. So we said that ciphers use the same rounds many times. The question is how many rounds a cipher should have. Unfortunately, there is no direct answer because there is no scientific answer for that. The common belief is that increasing the number of rounds increases the security. This is true in most cases, but there are some cryptanalysis techniques which work regardless of the number of rounds because they rely on the symmetry on the design. But in most cases, this belief is correct. If you increase the number of rounds, it becomes more complicated. So it becomes harder to attack. So it becomes more secure, but it will decrease the performance. So you have to find a sweet spot which provides good security and good performance. A common practice is as follows. Designers apply every known cryptanalysis techniques when they design a cipher. And if they can break at most n rounds, then they choose the number of rounds are as larger than or equal to 2n to stay on the safe side. So when you design a cipher, assume that you can break 10 rounds. So you say that, okay, let's design the cipher to be 20 rounds. Because even if you could break 10 rounds, some people will find another weakness and break 11 rounds or 12 rounds and so on. So this is why there's this kind of common belief, because attacks always get better. People come up with new weaknesses, they observe new weaknesses, they come up with new cryptanalysis techniques all the time. So in order to provide the security, we should be constantly, checking the security. When a new cryptanalysis technique is introduced, we have to check older ciphers if they are secure against this newly discovered technique.